Okay, then let's make a start on the next session. This session will be about bending and shear, and it also says and axial load at the end there. And if you look at the notes, you will find that there is a section on bending, shear, and axial load. But I think I'll probably skip over those few slides because it just starts getting slightly ridiculous, and it's very difficult to try to explain it so that other people actually understand it. So I think we'll concentrate on the bending and shear and the bending and axial load, and I'll leave you to look up the interaction between bending, shear, and axial load later on, because it's just better to get your head around it that way. Okay, so starting off with bending and shear. Basically, the shear forces acting on a steel section can reduce the bending resistance of the section if the shear force is large enough, and therefore it's necessary to consider the interaction between these two actions. The interaction will depend on two different things. First of all, the class of the section, and second of all, whether the section is susceptible or not to shear buckling. The plastic moment resistance is used even for class 3 and 4 sections, and that's basically because the testing that's been done has shown that the reduction due to the shear on the actual moment resistance is actually very, very small. So this is one of the areas where you will actually find a big benefit using the Eurocodes compared to the BS5400 approach. You'll get a lot more out of your shear moment interaction than you would have done to BS5400. And this is also quite useful if you're doing a sort of strengthening scheme, or we have used it quite a lot for assessments and things like that as well. It's proved to be quite a useful tool to use. The first thing we'll do now is we'll start off looking at class 1 and 2 sections, and we'll consider a case where we don't have any shear buckling. And basically, it's the sort of easiest case to start considering. And basically, if the shear force is less than half the plastic shear resistance, you don't have any interaction at all with the moment. If you have a shear force that's greater than half the plastic shear resistance, then you have to allow for some interaction with the section. And you need to take that into account by reducing the yield stress in the section for the bending calculation. And you do that by applying these two formula there, and that just acts essentially as a reduction factor onto the bending resistance. This VED factor is an applied shear force. The VPL is just the plastic shear resistance. Alternatively, you can use the second formula shown there, which is essentially just reducing the web strength. And potentially you could just reduce the thickness of the web by the same sort of factor. So there's a couple of different ways you can sort of reduce the web strength and take into account the interaction. However, once you've sort of started reducing web thicknesses and things like that, you shouldn't then go back and reclassify the section. You should just use that section for this interaction only. You don't go and redo any of the rest of the calculations in there. The code does give some simple formula for equal flanges and sort of simple I-beams, but if you have a typical bridge, it's not very often that you've got an isometric beam. They just don't seem to happen very much in bridges. So that's more applicable for building design, really. If you're dealing with bridges, you have to sort of use a revised plastic resistance moment, and that's just found by determining the plastic neutral axis and calculating the moment resistance about that axis for the reduced say the section properties that you calculated there. So it's a little bit more calculation if you don't have a symmetrical section, but generally speaking, it's kind of what you're stuck with if you're doing a bridge design. Okay, so this slide here will then just show you the interaction between this moment and the shear. And as you can see, there isn't actually that much interaction between the two. Well, below the half the plastic resistance, you have no interaction, and below the plastic bending resistance, you don't have any interaction either. It's just in this zone in there where you do have some interaction, and that interaction is quite a lot more quite a lot better than it is in BS5400. The difference is less for class 1 and 2 sections, but it's bigger as we go along, and I'll sort of show you the diagrams later on for the other sections. For the class 3 section, again, as I said, the diagram is based on the plastic moment resistance, even though it's the elastic resistance that will govern your sort of the moment design within that section. But as you can see, once you actually, if you have the elastic moment resistance, you just draw a vertical line up to where that line intersects the interaction curve, and that's then the interaction that you get. If you had BS5400, the interaction would be basically draw a straight line between the plastic shear resistance point up there and the elastic moment resistance there, and you'd end up with a lot less allowance for interaction in that region there. And as I said, this has been proven through quite a lot of testing, so it is quite safe. And it's just based on sort of the stuff that's being done much more recently than when BS5400 was written. If you do have shear buckling within the section, you have slightly different interaction criteria that apply. And basically here again, if the shear force is less than half the web shear buckling resistance, you don't have any shear interaction between the moment and the shear. But if the shear force is greater than half the web shear buckling resistance, you do have an interaction, and the interaction is then shown in this equation there on the slide. And you have to apply these different ratios. So you got the N1 bar is the ratio for the moment resistance, and the N3 bar is the sort of interaction from the shear resistance. And you take that and then use that to develop your interaction curve. The full web shear resistance contribution is then just obtained for the moment of where the moment is less than MF, RD, and the actual interaction that you get is then shown on this diagram here. So as you can see, it is a little bit different from the section where we had no shear buckling, because you've got a bit of a curve to this part of the curve, a bit of a curve up here, but otherwise it's essentially a very similar interaction and using sort of slightly different numbers. But again, you do get quite a lot more benefit than what you had for BS5400. And that's just a diagram there for the class 1 and 2 sections. The class 3 section is derived in exactly the same way. It's only that instead of extending the curve out to the plastic moment resistance, you just curtail it at the elastic moment resistance of the section. And the same thing is done if you're using a class 4 section as well. Only difference is for class 4 section that you base the sort of resistance for the moment on the sort of MPL, RD and MF, RD. On the gross web area and the reduced flange area within the sections. And as I said previously, pretty much all these curves that you've seen on these couple of slides will give you a better interaction than the ones that you would have seen in BS5400. So it is really a very useful tool to be sort of getting that extra bit of capacity out of something. And we found it particularly useful for assessment and strengthening schemes, where, particularly for strengthening scheme, where you've sort of found you need a whole bunch of extra stiffness to sort of strengthen up a web in an old box girder or something. You start applying these equations, and suddenly you can get rid of a lot of the interaction requirements, and you can therefore get you can therefore reach a point where you don't have to do nearly as much strengthening on the section. So clients quite like you're using this sort of stuff. The Eurocode does not require the interaction between bending and shear buckling to be verified at sections nearer than the height of the web divided by 2 to a support if you've got a bearing stiffener. And basically the reason for that is that the chance of buckling very close to a stiffener is very, very low. It generally speaking, a steel plate will not buckle immediately adjacent to a stiffener. It'll start buckling sort of further away from it. And Eurocode states that the area where it starts being susceptible to buckling is the height of the web divided by 2. So it's basically you have to check web buckling at that point there. You don't have to check it at that point there. Again, that's another area where you can get some benefit out of the code. You will still need to check the interaction at the support for the plastic shear resistance though, and you have to base it on full plastic shear resistance there because the effects are still there. It's just the buckling effects that you can sort of check further away from the section. For a composite section with a class 1 or 2 section, the interaction is considered by reducing the web area even where there is shear buckling, and this differs slightly from the approach for pure steel sections, which uses that interaction formula instead. In practice though, even though the methodology looks slightly different, it doesn't really give any different answers. It gives you pretty much the same sort of result. This slide here goes through class 3 and 4 sections, and it's not actually correct anymore. There's been an amendment to Eurocode 4 that's come out, and I think it came out a couple of months ago, that basically makes this slide redundant. It's no longer accurate. And the part of the Thomas Telford guide that discusses this is also not accurate because it was written for the code before it was amended. So that's quite an important thing to note. So basically everything on that slide is not really correct anymore. And instead of modifying the moment in the way that's sort of mentioned on this, you just use the full actual moment within the section. So again, just something to make sure you're aware of, and when you do come to that part of the Thomas Telford guide, to write yourself a note to say this is no longer what we're doing, because the code's been modified since then. Okay, the flanges in the box girders. The equation that's shown up there can also be used to verify the flanges in box girders, and it is exactly the same interaction formula that we were looking at sort of earlier. The difference here is that MF, RD should be taken as equal to 0, and basically that just means that the webs are not allowed to increase the shear strength. The N1 bar is replaced by N1. Again, there's no actual test evidence to suggest that the plastic bending resistance can be used when checking a wide flange, and that's why it's been replaced. And the N3 bar value is determined as the greater value obtained from overall flange shear buckling or for the sub-panel buckling. And again, that's just shown on this slide here. Now going on to look at the bending and axial force within the section. Generally speaking, the presence of axial force will reduce the ultimate bending resistance of a cross-section, where the parts that contribute to the bending resistance are also required to resist the axial force as well. If you do have an axial force, it is important to be consistent between the global analysis and the cross-section design, particularly with respect to the height at which the axial force is assumed to act. If the axial force is acting slightly eccentrically to the centroid, you will end up with additional moments being caused by that axial load, and those moments do have to be taken into account in the design. If you're using plastic design to derive an overall stress block within the section, it may sometimes be preferable to refer to refer the axial force to the plastic neutral axis obtained in the absence of an axial force. But again, the method of the interaction will be very dependent on the class of the cross-section, and it will vary depending on if you've got a class 1 and 2 or 3 or 4 type cross-section. For the class 1 and 2 sections, they're fully plastic, but generally speaking, they won't be very common in bridge design. We generally end up with class 3 and 4 sections. However, the class 1 and 2 sections can develop full plasticity throughout the entire depth of the section, and that complicates the check of the cross-section, as the stresses from the bending and the axial force can't simply be superimposed if advantage is to be taken of the plasticity within the section. Instead, to calculate the reduced plastic bending resistance where there's axial load present, you need to calculate this Mn, Rd factor. And basically that is just the MPL, Rd, which is the plastic moment resistance of the full section, minus MPL, X, which is just the plastic moment resistance of the section component, which is resisting the axial force. And you then use that in your design. The code does give some formula for the rectangular sections and beams with equal flanges, but again, it's not very common to have symmetrical sections for a bridge. And so now we'll just go over a bit more of a general method, which can be applied to bridge members in particular. So in cases where you've got a non-symmetrical section, you have to consider where the axial force determined from the global analysis is assumed to act. And this is particularly important as the elastic and the plastic bending neutral axis won't be at the same location for the cross-section. Using this method, the axial force is assumed to act at the plastic neutral axis in the absence of an axial force. If it acted at the elastic neutral axis, an additional moment would then need to be considered for the global analysis of the section, which would make things a little bit more complicated yet again. So do make sure that you apply it at the plastic neutral axis. For this, you calculate depth A, and that is just determined such that NED is equal to the height, which is A, times 2 times the yield strength of the steel. The next thing we have to do is calculate the moment resistance, and that's defined as M2, FYD. The reduced plastic resistance is then calculated, and that's just this Mn, Rd that we were discussing a bit earlier, which is just the plastic resistance minus M2 FYD that we said. Once you've done this, it's important to check that the section is still a class 1 or 2 section using the new plastic stress block, because otherwise you'll have to consider it as a class 3 or 4 section depending on what the reclassification of the section shows. In a lot of practical cases, the steel section will be subject to axial force as well as bending about both the axes within the system, so you'll have biaxial bending as well as the axial load acting on the section. And calculation of the collapse load is also complicated by the addition of moments about both axes. For this calculation, we can use the same principles as we've been through over the last couple of slides, where we just reduce the moment resistance by removing components to resist both the axial load and the biaxial moment. And there is a formula that is provided in the code, and that's the one shown on this slide here. And basically that just takes the applied moments in each direction and divides by the plastic resistance in that direction as well. And then this plastic resistance is then the resistance that has been reduced for the axial load as well. The alpha and beta constants that are given up there can conservatively be used as 1, or you can calculate them in a bit more detail. The code does give some values for sort of typical cross sections with I-beams and H-beams and channels and RHSs. But again, they're probably not very useful if you're doing a bridge design because we don't use them very often. We tend to have more complex sort of structures. or in more complex geometries. If you want to avoid the complexity of calculating the plastic stress block for the bending and axial force, there is a simplified linear interaction that you can use, and that's also given in the code by that sort of equation shown there. And if you've been using BS5400 previously, it'll be quite familiar because it's pretty much the same interaction curve. If you've got a separate section classification that you've done, you need to determine the plastic stress block. And it's quite often that if you sort of do a sort of separate calculation for the bending alone and the axial load alone, you find that the section will quite likely be a class 1 or 2 section for bending, but it'll be a class 3 or 4 section for the axial load. And you do need to take that into account when you do the calculation, because in the event where you have a class 3 or 4 section for the axial load, you can no longer use this simple interaction formula, and you have to do some more complicated equations, and you have to start determining the actual stress block that you get under both the combined axial load and moment that you have within the section. And you could potentially end up having to reclassify this section. For class 3 sections, these are a lot more susceptible to local buckling. And the plastic interactions of axial force and bending moment that we were discussing for the class 1 and 2 sections can't be applied for the class 3 sections. Instead of those formula, you have a simple superposition of elastic stresses, and the resulting stress is limited to the design yield strength at all locations within the beam, and that's just in accordance with the equation shown on this slide here. And in cases where you've got biaxial bending, you've got this interaction formula shown on the right-hand side there, where it's just dependent on the applied moment and the section moduluses in each of the directions that you're looking at, and of course the axial load and area of that section.
So W is section modulus?
W is essentially Z. You will find when you go through the Eurocodes that some of the things have been changed, some of the letters. I think R is now I, and things like that as well. It's sort of little things that have changed that can be slightly annoying because you no longer know what they are. And that is one of them. W is Z, essentially. If you've got a class 4 cross-section, these are treated in a very similar way to class 3 sections, but you use the effective section for the plate buckling. Your effective area and section modulus can be derived separately for the axial force and bending, or they can be derived for the combined stress distribution. If you are deriving it from the combined stress distribution, it will typically not be very practical, as it will require recalculation of the section properties for every different load case that you've got, and it basically means that you'll have to do quite a lot of iteration. It could potentially give you some increase in the economy though, because it gives you more accurate answers and isn't quite conservative, quite as conservative as other methods. And if you've got a spreadsheet or something like that, it may not be that difficult to do. And generally speaking, the formula given here are the ones that are used for the interaction formula. And again, there's a sort of a component in there that takes into account the eccentricity of the axial load on the section, and just adds it on to the moment on the moment resistance of that section. If the stress varies along the length of the panel, the verifications can be done at a distance of 0.4a or 0.5b from the panel end. But you also need to look at sort of the section at the actual support. We're using the gross section properties, and basically it's sort of a similar thing as we were discussing previously. It's not very likely to buckle if you've got put a restraint in, or such as a stiffener. So you are allowed to move a certain distance away just to check that, and just check the section there for the buckling. But you have to check it at section A using the gross section properties as well if you are going to use that approach, because that could potentially be slightly worse. Okay, the next session here is the bending, shear and axial load, and as I said in the beginning of this presentation, I won't actually go over any of this in any detail whatsoever. It's much better if you take it away and look at it yourself, because it is quite involved and it's very difficult to explain trying to get all these different effects in together. It's basically there so you have an awareness that it does exist, and you do need to take it into account when you do the calculations. So I'll just skip over these slides here and skip straight to the summary slide at the end. And this summary slide is quite useful really, because it tells you which clauses most things are actually considered in. So if you are looking at a class 1 or 2 section, it tells you which clauses you have to go to if you're looking at shear buckling, and it tells you which clauses to go to if you don't have any shear buckling, and then tells you what the interaction formula for bending and shear, bending and axial load, and bending, shear and axial load. So it's quite a good summary sheet really, and just gives you some useful information aware in the code to look for things. On that note,